Okay, so now we start talking about the theodolite, and here is a theodolite with us. What we will do first, we will start with the parts and construction of the theodolite. As I told you that the theodolite is basically for angle measurement, the horizontal angle measurement and the vertical angle measurement. Well, looking into the parts of the theodolite, first of all, if you begin, we will begin from the tripod. Tripod is these three legs. We make use of these three legs in order to support the instrument on top of it. We will talk about the tripod later on. However, in the tripod, besides these three legs, we have the tripod head. And in this head, we will see it in some more advanced kind of tripods. There is a centering head. So we will see that centering head and the use of that later on. Now coming to the theodolite, here in the theodolite, the bottommost plate which is fitted to the tripod, over here we can see this is called trivet. Trivet. On top of the trivet we have leveling screws. Now where are the leveling screws? There are three leveling screws here, 1, 2 and 3. We will see later on that we can make use of these screws in order to make the theodolite horizontal. What is the use of that? Why we do it? We will see all these things later on. But these leveling screws can be rotated in order to raise or lower the instrument, or the leveling, to change the leveling of the instrument. On top of that, we have a plate that is called triback. Now this plate is the triback. If you go further up, so going further up over here, I can rotate it also. So what is there? Over here is a horizontal circle and it's a graduated circle. If I draw this, it looks like a circle like this, and it is a glass circle made of glass, and it has got the graduations starting from 0, 90, 180, 270 and so on. So all these are the graduations. So this is called horizontal circle, and we make use of this for measuring the horizontal angles, as we will see in a moment. Now further on top of this, top of the horizontal circle or horizontal plate, we cannot see right now, but we have two windows here, one little window here and one little window on this side. Now these two windows are basically to see the readings, because as I was saying that we have the horizontal circle here, we need to read the angle values in this horizontal circle or this graduated circle. So to read this horizontal circle, which is inside this cover, this is all metal. Inside this metal, to read it, we have to look through the eyepieces. So these two are the eyepieces, two diagonally opposite ones. We say generally one near A and one near B for these eyepieces. And using this eyepiece, I can focus it for my eye. And after focusing it, I look through it and I can see the reading there. Now it is very obvious, if you are seeing the reading, what we are seeing it about? Well, in the case of this horizontal circle, there is one additional thing, which we say index. Index may look like this. What is this index? There in the horizontal circle, we have the graduations, and depending the type of the theodolite, these graduations will vary. While in the index, again further we have the graduations, and basically the job of these two is to serve as vernier. This particular assembly here, A, and this one here, B, they ensure that the observations are taken with better least count. We will see this also in a moment. Now what happens, how it is measuring the angles? What is the thing which is happening there inside? We will try to look into that part now. Well, you can see, if I can show you by my hand also, That's the horizontal plate or horizontal circle, or we say lower circle also, because this is the lower one. On top of this is the index. This assembly which I had just plotted, this is also called index or vernier arm. Well, the index A and B vernier. Similarly here, for example, we can imagine, let's say this is A index and this is B index. That's the horizontal circle. Just for the sake of showing you here, I'm showing you like this, otherwise in the instrument it is this way. Now, when we measure the angle, we rotate our theodolite and we are sighting through this telescope. We will see this telescope in a moment. So, we rotate it. So, basically what is happening? If for example, let's say this is 0 degrees, the reading initially for this vernier and this vernier are 0 and 0. We rotate our telescope, so what happens? Our index rotates. So once this index rotates, the reading against this vernier over here, this angle, and for this vernier, this angle changes. So what happens? By rotation of this, we are able to measure the angles. So basically, that's my horizontal circle. The initial location of the vernier was like this, vernier A and vernier B, and there is some value of the reading. Well, later on, after rotating the telescope, the vernier A may reach here and vernier B may reach here, and now it will see the corresponding observation or the reading. So the angle at this point can be seen by reading these graduations. Well, what was the value of the observation here, and what is the value of the observation over here? Now the difference of these two will give us this particular angle. So this is what is happening there inside the instrument. Well, regarding the construction of this, to show the construction, I will draw a diagram. Okay, here is a diagram, and in this diagram what I have tried to show, I am trying to show you how the instrument is constructed. Because here in the instrument, as you can see in the diagram here, we have first this edge and this is the upper plate. Upper plate means the index or the vernier. We have also down here, and this, because this is the cross section of the instrument, and this is the lower plate or the horizontal circle, which is the full circle as we are seeing. Well, we have the screw A, which we say upper plate clamp. So this screw A is upper plate clamp, and this B is lower plate clamp. Now what is their role? If you can see in this diagram also. Well, let's start doing it. If you, for example, unclamp this B, if this B is unclamped, that means B comes out to this direction, this way. This is how the B comes. If it is so, what will happen? This upper plate as well as the lower plate, they are free now from this block. So if I rotate my instrument now, so upper plate and the lower plate both will rotate, because this A is clamped right now. Now if I release this A also, I release this A, so A also comes out in this direction. What will happen? The contact between the lower plate and the upper plate will be lost. Now in this case, if I rotate my instrument, only the upper plate will rotate. So the case is, I have clamped this B, I have unclamped A, so now this total assembly, because I have clamped this B, so this lower plate is clamped with this spindle, while this upper plate is free to rotate. because we have taken this A towards this side. So in rotating the instrument, only the upper plate will rotate. So how do we do with this with the instrument? Okay, here in the instrument, if you see, we have the upper clamp and the lower clamp. Right now, I have, if you can see it better this way, this is the lower clamp and this is the upper clamp. I unclamp the lower one, now I rotate the instrument. The upper one is clamped. So what is happening in this case, both the horizontal circle and as well as the index, both are rotating together because the lower one is unclamped and upper one is clamped. So both rotate together right now. Well, I clamp it. The lower one is clamped. Lower one is clamped means this is now, it can't rotate. And upper one, I unclamp. That means the upper one is free to rotate. Now in this case, if I rotate my instrument, it is still rotating. But the bottom plate is stationary. It's not rotating. The only rotation is in the index arm or the vernier arm. Only this is rotating. And this is why you can guess it very well. If my upper is clamped, lower is unclamped. Mind it, both are fit together. Now I rotate the instrument. Is the angle value changing? The angle value is not changing because what is happening here? Both of them, they rotate like this together. So the angle value means the readings against vernier A and vernier B, it's not changing. But by clamping the lower one, unclamping the upper one, the rotation is like this and the angle values are changing. And this is what is happening here. So this is how you can change the angle, the readings, and this is how you can observe the horizontal angle. We'll see more about this in a moment. Now along with these clamp screws, for example, we saw this is the upper clamp. We have one more screw here. This is called upper tangent screw. Upper tangent. Similarly, for the bottom plate also, bottom clamp, bottom tangent screw. Now what is the role of these tangent screws? This will clamp the motion, but many times to bisect the ranging rod, which we are sighting through the telescope, we need to give very mild rotations to the instrument. So those mild rotations can be given by the tangent screw. So this is why we have got a tangent in both upper and lower. Well, we go further up. Having understood this, construction of the bottom plate, upper plate, angle measurement, we look through, this is vernier A, vernier B, these are the glass windows here, so that I can see inside and I can see these verniers and readings. If you go further up, here is a bubble tube. What is this bubble tube? Bubble tube, as you might have seen somewhere else also, is a part of a large tube which is circular. So we cut a little part of that and this part is the bubble tube, something like this, and this is filled with some liquid. We'll see later on about the bubble tube, what this liquid is, what should be the characteristic of the liquid, this we'll see, and a little space is left there. Now this little space over here serves as the bubble, or this little air, it serves as the bubble. So depending if my bubble tube is horizontal, or maybe let us say this line is called the axis of the bubble tube, tangent at this point. If this line is horizontal line, the bubble will be in center. How the bubble looks like in the plan view? That's the plan view of a bubble tube. Well, here inside we have the bubble and there are some graduations. And the bubble may appear like this. Right now the bubble is not in center because center means it has to be here. And if we make this bubble in center, the air bubble will come over here, and once it is in center, this line is horizontal. So this is how we use the bubble tube, and a similar bubble tube is fitted here because we want to ensure that this plate is horizontal. We want to measure the angles. All the angles are to be measured on a horizontal plane. We want to make this plate horizontal. That is how we make use of the bubble tube. So we will see about this in a moment. Well, going further up in the instrument, if you go further up, we have these parts are called the standards or A-frame. Standards or A-frame, and they support, you can see over here a standard here, and they are supporting on the horizontal axis. This axis of the instrument, you can visualize it here, an axis of the instrument here about which this telescope rotates. You can visualize a line passing through here. This is the horizontal axis. So this standard or A-frame supports the telescope. Furthermore, there are more interesting things here. We'll talk about the telescope later on. Well, what I can do here, I can rotate this telescope. As we have seen that while we are measuring the angle, particularly in the vertical angle, we need to sight some object, for example, like this. And this should give me the amount of the vertical angle for a particular point here. So how do we observe that vertical angle? Well, you can see here, similar to the horizontal case, there in the vertical also, we have a plate attached to the telescope. So if I am rotating this telescope, along with this, a plate is also rotating. The construction of this vertical circle is, we have a telescope, as we can see here, that's the telescope, and as I told you that while we are rotating this telescope, along with this, a vertical circle is also rotating. Where is this vertical circle? This vertical circle is something like attached with the telescope, and this vertical circle is graduated. I just show it like this so that you can have a feel of the telescope there in behind, and that's the vertical circle, and we have the graduations in the vertical circle. These graduations may start from 0, reach 90 degrees here, again may have 90 degrees, or maybe a different arrangement, 0 to 360, 0 to, depending the theodolite. But right now I am taking it as 0 and then 90 degrees here and there. So this is the graduated circle. Okay, when we are rotating it, what is happening? This is the telescope and that's the vertical circle, and both of them, they rotate together. So how we are measuring the angle? What we are doing in order to measure the angle? There should be a reference, there should be an index. We need something called the index. And as we have seen, for our horizontal angle measurements, the vertical angle measurement, the reference is the horizontal plane. So somehow we need to establish that horizontal plane or horizontal line here. So in addition to this telescope and this vertical circle, we also have an additional index frame here. That index frame looks like this. Now what is this index frame? This index frame, basically we say one near A and one near B, and the line joining one near A and one near B will be a horizontal line. So while we rotate our telescope, this vertical circle also rotates, but our index remains stationary now. Well, so this is stationary. These 2 points, the one near A and one near B, they give us a horizontal line of sight, and I am rotating my vertical circle with the telescope. Well, initially, let us say the reading was 0, 0. My telescope is horizontal. My telescope is like this and the reading is 0, 0. Now I rotate my telescope, so my vertical circle will rotate. So the angle between these two will be the vertical angle, and this is what we are doing here. By rotating this, we can see it again using these eyepieces. We could not see those windows in case of the horizontal circle, but we can see the windows very well in case of the vertical circle. So this is window for one near A, this is a window for one near B. So by making use of these windows and these eyepieces, I can again focus this eyepiece to my eye, and we can see through this and see the readings. So right now for horizontal line of sight, the reading should be 0, 0. If I change it, as the angle is increasing, the reading will change. Now, in order to ensure whether it is horizontal or not, because our line of sight, our reference for vertical angle is horizontal line. How do we ensure that this index frame, it is inside, is horizontal or not? In order to ensure this, we have an additional bubble tube here. It's a similar bubble tube to this, but it is more sensitive. We'll talk about the sensitivity of the bubble tube later. But using this bubble tube, we can make our index horizontal. So basically, the bubble tube is kept on the index. So by making this bubble tube horizontal, this index can be made horizontal. So we can draw it here in the diagram also. Over here is our bubble tube, and this bubble tube is called altitude bubble tube. And you know, we have understood that we make use of this for measuring vertical angles. Well, we will see some more parts of this theodolite. Here in the vertical circle, what can I do? I can clamp it. Clamping means in this particular theodolite, it is here. Once I have clamped it, I cannot rotate my telescope. But using the tangent here, so this is the screw for vertical circle clamp, and this is the screw for vertical circle tangent. So this is vertical tangent screw. So using this, still I can rotate my theodolite, but by very small amount. While if I want to do it with large, I can use this one by unclamping this one. Now here also, in the case of the telescope, if you look at the telescope, we'll look into the optics of the telescope next time. But today, this part of the telescope is called the eyepiece because I keep it towards me and I look through this. And mostly, whenever we set this instrument, we should ensure that the instrument is set in such a way that the eyepiece is at the height of my eye or the eye of the observer. Why is it important? Because if you are working in the field and if this instrument is set in such a way that your eyepiece is here, so every time you have to go up in order to take the observations, or if it is down, you have to bend. So this is not comfortable, because when we work with the instrument in the field, we work for hours. So we should set to a comfortable height, as in this case. Without any bending or without anything, I can see through the eyepiece. Well, over here is the objective. So using this telescope, we can see and we can focus the eyepiece over here and focus the objective using this screw. So this is objective focusing screw. We'll talk about the focusing phenomena. What is going on there inside? How the focusing taking place in our next lecture. Well, along with this, if you look at this telescope very carefully, over here, there is a little V and there is a little I. If I draw it here, what it looks like, there is a V and there is an I. Basically, why we use it? The V is here and the I is here. We use it, for example, if I need to bisect an electric pole or a ranging rod, the field of view of the telescope is not big. The field of view for a human being is very wide. I can see that ranging rod there. But once I start bisecting that using the telescope, I will have to do many iterations of rotating it in horizontal, rotating this in vertical. Then only I will be able to bisect a particular point. So in order to save our time there, this target sight is provided, or this is also called rifle sight. As you might have seen, over all the rifles, this kind of sight is there in order to aim. So here we make use of this. We make use of the V and the I, we make it a W. And then we take this W to that particular object. Because once we are taking that W, our field of view is very large. So we can that way bisect the object fast. Along with this, over here, As we are talking about, we have our index here, vertical index arm, and in this vertical index arm we have the altitude bubble fitted there, and this index arm becomes the reference for vertical angle measurement, and we want to ensure that this index arm is horizontal. Sometimes, after working with the instrument, it might happen that this is not horizontal anymore, it has tilted. How to bring it back? To bring it back, we have one more screw here. We use this screw, and this is called clip screw. This clip screw is basically fitted here. By rotating this clip screw, it is possible that we can rotate our index frame and we can make it horizontal. So this is the clip screw. One more thing which you will observe here, all these screws are milled differently. Here it is smooth, over here it is very coarse milled. This particular screw is very coarse milled, and this is very fine milled. Why is it so? Whenever we are working with the instrument, for example, if I am looking through the instrument, I am trying to bisect something and I want to use a particular screw. For example, I want to use the clamp. So it might happen, because I am looking through the theodolite, it might happen that by accident I touch the tangent. So if this happens, the angle value will change. So in order to give us an idea, okay, while we are looking through the eyepiece, we are engrossed in our work, just by moving our hands here and here, by feeling these different milling of the screws, it is possible to work without looking at these screws. This is why the milling is different. And similarly here, the milling is very, very different, because we don't always want to use the clip screw. In order to use this clip screw, we have to use some additional needle, then only we can use it. So this is why the milling is kept different. One more thing about this theodolite, I can rotate this theodolite through 180 degree. Okay, as you can see here, I can rotate it. This kind of theodolites which we can rotate are called transit theodolite, and this procedure is also called transiting the theodolite. So we are transiting the theodolite. Well, in addition, if I am rotating my theodolite in horizontal circle like this is called swinging. Swinging in horizontal and transiting in vertical. Now along with this, one last feature here at the top, over here, this is a mirror. Now what is the use of the mirror there? In this particular strip, a mirror is fitted, and down there is the bubble tube. Because my eye is here, I cannot see this bubble tube. So in order to see the bubble tube, I have to go up to see whether it is in center or not. So in order to avoid that, this mirror is fitted here, and I can see comfortably from this side only whether the bubble is in center or not using this mirror. And this is why the mirror is fitted there. This particular instrument which we saw today is the vernier theodolite. It has a vernier setup to take the observations. The least count is 20 seconds. You will find in the field different kinds of theodolite, and all those theodolites, they need to be read differently depending upon what the instrument is. And you will find the instructions in the manual of the theodolite, how to read that one. But the vernier one, which is very common one, we'll see that how we read the vernier one now. Well, as we have seen in the case of the vernier one, as we can see here, this black one is the horizontal circle, or it may be the vertical circle also, and this AB is the index, either in the case of the horizontal circle or in the case of the vertical, in any case. And what we do, we read the theodolite or the angle value against these verniers. That what's the value of the reading. How to take these observations, we'll see that now. In case of our main scale, if I am showing the main scale here, in main scale the graduations are written in such a way that, let's say if this is 10, 11, 12, 13, 14, 15, all in degrees. we have got further subdivision. So each degree is divided in further divisions of 20 minutes. So the least count of main scale is 20 minutes. So if you are using only the main scale, we can use up to 20 minutes. But this is fitted with a 1 year. As you can see here in this case, this A and B are 1 year. How these 1 years are actually there and how we improve the precision using these 1 years. Now in these 1 years, now this particular part of 20 second here, if you just look at this or any little graduation, this is for 20 minute. I expand this 20 minute and I am showing you here now this 20 minute. So 0 and 20, so this is 20 minute. Now in this 20 minute, we have the 1 year, and in 1 year designed in such a way that because in this 20 second, we have 60 graduations of 1 year. So 59 graduations on the main are equal to 60 graduations on the 1 year. So this is actually, you can make use of this in order to find the least count of that. Now how we take the observations? Here it looks like this. We can say 5 degrees, 6 degrees, 7 degrees, 8 degrees, 9, and that's our 1 year here. This is the main scale, and in 1 year and in main scale, the graduation which meets or which gets aligned is over here. I point it. So what is the value of the reading? Well, first we read in the main scale. So in the main scale we have passed 5, 6 and 7. So reading is more than 7 degrees, and then also we are at this 20 minute. So 7 degrees 20 minute is the reading from the main scale. So this is from main scale. Then in the 1 year, that's the graduation which is aligning with the graduation of the main scale. So what is the value there? We have 6, 7, 8, because this total is for 20 minutes. We have passed this 8th one. We have passed further. If you can see in the 1 year, each minute is further divided in 3. 1, 2, this should be 9 here. So it is further divided in 3. One part, second part and third part. So each is corresponding to 20 seconds. So you can see the least count in the 1 year is 20 seconds. Well, what is the value of the angle? The angle here in this case, we have passed this 8 minutes already. 8 is per minute. From 8 to 9, in between our this red line is there, which is the aligning mark, and we have passed 1 and 2. So the 1 year says the reading is 40. So the total reading will be 7, 28 and 40. 7 degrees, 28 minutes and 40 seconds, because 20 seconds is the least count of this instrument. So this is one way of reading the 1 year. Now there are different kinds of reading devices. There are some electronic also. If you are talking about the electronic instruments, there are some electronic devices which can read the instrument, which can give you the angle value. There are different kinds of constructions. The idea is, one could be, which is used, a circle is there. This is a circle in glass, and they are very fine graduations. Very fine graduations are there, and underneath this glass, if this is the glass, we have the graduations etched into it, some 20,000, and underneath there is a photodiode which is emitting the light, and the size of that photodiode is same as the size of the graduation. All these graduations are basically the black and white lines like this, very fine. So what happens, we initialize it at some value, and then once we rotate it, the light which is coming out of it, because somewhere the light will pass, somewhere it will not pass. So what the light will do, it will generate a sinusoidal wave kind of thing. The light is there, it's not there. The light is there, it's not there. So counting these and further, doing some further, we can take the observation here, take the observation here, the waveform generated here and the waveform generated here is superimposed in order to achieve better precision. So this is how, it can give the accuracy of the order of 1 second also, or the least count, the precision. This kind of precision is possible with this electronic device or electronic measuring plate. So we have varieties of these. So what we have seen today is starting from the beginning. We saw the significance of the angle, because we need angle measurement in horizontal and vertical for many purposes. Then we saw that we need to measure more precision, because we need to have compatibility of the instruments. Somewhere you need more accurate results, more precise results. So we need to go for the theodolite. So in the case of the theodolite, we saw that it is really a very good instrument, very useful instrument in surveying, and we can carry out, as we saw in the case of the theodolite, the horizontal and vertical angle measurements. We saw the various parts of the theodolite, starting from the tripod, trivac, leveling screws, trivet, horizontal circle, index arm, and so on, up to the telescope and the mirror here, altitude bubble, everything. Then we saw how we can take the observations using the vernier theodolite. I know it's difficult for you to understand it directly from the video screen. Please visit your laboratory or wherever you can find a vernier theodolite. Go and observe it. Handle the various parts yourself with using your hand. Then only you will have a feel of the instrument and observe the vernier theodolite yourself. See the readings. This is how you will know about the instrument in full. Well, we end our this lecture today here. Thank you very much.